Share my slide. Okay. Good morning, everyone. My presentation will mostly targeting the diagnostic technologies, and I'll try not to dwell too much on things that you can find in Wikipedia, and more on the facts and what you maybe will not be able to find or understand via your own study online. But before we start, we truly need to know coronavirus, there are actually 4 different types. Okay, there are alpha, beta, gamma, and delta coronaviruses. There are 4 of them, and the 2 that I highlighted here, alpha and beta, they are of public health importance because it causes flu-like symptoms, coughing, and anything that's similar to SARS-CoV infection. And there are 4 of them that has been circulating since the 1950s, the 229E, NL63, OC43, and HKU1. The interesting thing is all these viruses has been found many years back, but diagnostic was or is rarely done until probably recently. Some private hospitals started to look for all these viruses too, just to exclude SARS-CoV. So I call these seasonal coronaviruses. If you read a lot about seasonal coronaviruses, from the beginning of the pandemic, you will know that this virus will actually go towards the same fate that is endemic in our society. And these are what I call the epidemic and the pandemic COVIDs. The SARS-CoV, this one is SARS-CoV-1, which was detected in 2002, 2003. And this is a recent popular one. MERS, basically, it is limited to the Middle East. Most of these viruses can be traced back to bat origin. The chronological discovery of human COVIDs. So you will see that 229E, OC43, NL63, and HKU1, these are what I mentioned just now, the seasonal coronaviruses. They were discovered since the 1960s. Okay, 2 of them in the 1960s, and the other 2 quite recently in 2004, 2005. Previously, it was thought that these viruses only cause mild flu-like symptoms, but deeper studies found that some of them can actually cause pneumonia and worse. And they said the first coronavirus was detected in 1937, which is not of a human. And the important one is that, and the date of discovery is stated here. When I teach virology, the first thing that comes to the student's mind is the schematic diagram. And we do need to know that how it looks like in nature before we can understand how we can detect them and how to study them. Under the electron microscope, you will find that there are spike-like protrusion, which we call it the spike. So the vaccine is based on the spike nucleoprotein. Okay, so the spike glycoprotein, sorry. And then there are other proteins like the nucleocapsid, the end, the membrane, the envelope, and the nucleic acid. The RNA nucleic acid is inside. Nucleocapsid, basically, you will see that it is bound to the genomic material. Okay, that's why it's called nucleocapsid. Spike and nucleoprotein, they are important. They were targets for vaccine development, but now most vaccines will only target spike glycoprotein. And you'll see later on that detection of SARS-CoV-2 is mainly targeting these structural proteins. So I call it structural proteins. Okay, structural proteins from the name structure, you know that is physical. You can see, and these try not to be overwhelmed by all the labels and other things. I want you to appreciate this is the genome of the virus. And there are two parts. One is the non-structural gene. The non-structural genes, it doesn't have a structure, meaning when it infects the cell, it gets expressed and then it will be used to hijack the cellular mechanism of your cell. Structural genes, they will form the structure, okay? And this is the RDRP, the RNA-dependent RNA polymerase gene. This one is the polymerase which makes more RNA for the genomic material. So this is the map of the RNA. And then when it is translated, they just amplify the spike protein here. You will find that the spike protein comes with two parts, the S1 and also the S2. And the important one is the receptor binding domain, the RBM or the RBD actually. This one is important for your vaccine development and diagnostic tests. Okay. So the full spike is much longer, but when people talk about the receptor binding domain, we are talking about a very narrow part of the virus protein. So I highlighted these three, the RDRP, E, and N. These three, if you have been to any hospital or the screening centers, because you will expose, the three genes will come out in your test report. And the S is mainly for your the vaccine development. And ACE2 receptor is important, the angiotensin converting enzyme 2. Okay, most of us, we just recognize it as S2 or ACE2. Dr. Lau mentioned this last week too. And the spike protein, or using the receptor binding domain, it binds to this ACE2 receptor and before it enters the cell. So the logic of having a vaccine is when you have antibody that coats around the spike glycoprotein, these virus particles will not be able to bind to angiotensin converting enzyme 2. Therefore, the infection can be aborted. There is another core receptor that helps the virus to get into the cell. This is less popular, the TMPRSS2. Okay. And we are very much experts in the Delta virus. Just now, at the beginning, I showed you the family tree of coronaviruses. And we also see that there are 4 different genus or genera of coronaviruses. They are the alpha, beta, gamma, and delta. The delta variant is different from the delta virus. Okay, and this delta that we are talking about today is a variant, a derivative from the Wuhan strain, or after many generations of propagation, it sort of adapts to certain condition, and it is genetically different from the original strains. And you may have heard of the variant of concern, variants of interest, and variants under monitoring. Probably this variant under monitoring is less popular. We are more concerned about the one that is of concern. So this is a scary family tree of SARS-CoV-2 alone. And this is what we call the next strain clade. The next trend, you can actually go to this website. It will just automatically generate this family tree for you. And you will see that 21A Delta is here. 21A, the green color. Okay, 21A, which is a Delta virus. Okay, previously it was only known as 21A. And then 21D eta, 21H mu, the gamma is here, lambda, and so on. It is plotted against time in a chronological order. So from February 2020 until recently, okay? And you will see that the gamma is of lesser quantity. Alpha, it was quite a big concern, but you will find the beta here in blue. This one, this blue one, you see that it was here before in Malaysia, but soon everything is decreasing radically. And most of our strain today, you get infected by SARS-CoV-2, they are all from the Delta variant, okay? And this is not surprising. And after this, we'll have different variants that will replace Delta. In virology, we call this the genotype replacement phenomenon. So when everybody gets vaccinated or infected by a certain strain, eventually there'll be a variant that can escape your antibody produced by the current vaccine. So Delta will be selected to be the main strains for today. And eventually, most of the population get infected by Delta. You have immunity against Delta, and other strains that can live with antibody against Delta will survive. So this becomes very difficult when we talk to public about 21A, 21D. So what are you talking about? And World Health Organization decided there must be a better way to number them or make it more easier for the general public to understand. You will see that this is a WHO level on the variants of concern only. And we have the alpha, beta, gamma, and delta. And then we have this Pango lineage, GZ clade. These are different, these four that is listed here. These are four different organizations that is championing on elucidating what variants are available now. So different organizations will use a different way to name. Like for this Pango, they call it the alpha, the B117. Previously, people call it the United Kingdom, the UK variant. And then we have the Delta from India, which is called the B1617.2. GZ call it differently. So they means the same thing. The amino acid change is the location on the spike protein, which there's a amino acid change detected. So the variants of concerns, they have high transmissibility. They escape public health measurement, and it spreads even though there's a vaccination and so on. So it's of concern. The WHO label basically helps everybody to understand it better. And there are also variants of interest. If you log into WHO website, probably a month or two ago, you may find a longer list. Because the variant of interest, they sort of form clusters, small outbreaks spread throughout certain countries, but it's sort of under control, or it may not increase the number of hospitalization. So they call it the variants of interest. And this variant of interest can quickly escalate to become the variant of concern if the number of hospitalization associated with that particular variant is being proven to be true. And some of the variant of concern can also be downgraded to variant of interest. And if there is really not much concern or interest for these variants, it will be downgraded to the variants under monitoring. To understand the technology, we need to learn a little bit about the viral and antibody kinetics. So this is the red color line represents the virus. So you see that at day 0, when you get infected by the virus, probably after 3 days, the virus will start to grow. And then there is a dotted line here. The horizontal dotted line represents the detectable cutoff value. And if you go for a swab test earlier, you may not get a positive result. But once it increased beyond the cutoff value, you'll be able to, the hospital and the lab will be able to detect it. And viral RNA via PCR becomes positive thereafter. When the virus increases, the IgM, the antibody called IgM, will also increase. When IgM decreases, IgG will increase. You will see that both IgM and IgG will decrease much later after the real infection and much later after live virus can be detected. Okay, so normally when you get sick and you are symptomatic, it represents the time where the viral load is the highest in your nasopharynx, not before. Where during incubation period, normally they're just trying to beef up the number of viruses, so you remains asymptomatic. Okay. These are a library of protocols that you can find online in WHO website. And for us in Malaysia, we normally will look at from the Germany protocol, which I call it the Berlin Protocol because it was initially known as the Berlin Protocol. And the target genes, if you go to different hospital, the report might be different. They might report the open reading frame 1A, B, and N, and so on. But ours, I'm more familiar with the Berlin Protocol. They use 3 genes, the RDRP, E, and N. Okay. Because this is a RNA virus, we use the reverse transcription, real-time polymerase chain reaction, and we look for the genomic RNA. It runs for 40 cycles, and the result reported as CT value or cycle threshold value. The CT is a cycle number where RNA is detected, and at low CT, meaning at very low CT value, the viral load is high, and inversely, high CT value indicates the viral load is low. And the sensitivity is extremely high. We can detect up to 10 to 100 copies minimum of viral RNA, and can be done in singleplex or multiplex. To explain a little bit about the protocol that we use, first, if we do a singleplex, meaning we screen for 1 gene at a time. The algorithm is when you screen for the E gene, the envelope gene, when it is positive, it says it is probably the 2002 SARS-CoV-1 or SARS-CoV-2. But since SARS-CoV-1 has already been extinct, it is most probably SARS-CoV-2. And then once it's positive, we proceed to the single confirmatory gene. It's either RDP or N gene. Okay, so you have the 2 confirmatory gene and 1 screening gene. During the initial part of the pandemic, where funding is not really that great, we really use some laboratories, not us, use the E gene first. And then once it's positive, they proceed to confirm it by using either one of these or both of these. And just now I mentioned about multiplex. So in the hospital in Kuching and all over Sarawak, we use the multiplex system, meaning in a single test, we detect the presence of E, RDLP, and N. This is what the result looks like on the computer. The important thing is the horizontal line here. You'll see that the CT value ends at 40. I can increase it to 45, 50. That is actually up to me. But generally, we think that 40 should be enough. So one cycle, if you can detect things in 10 cycles, that is very early. But if you detect it much later, that means you need a lot of amplification. The viral load is low. And if it's towards the end, then the viral load is probably very low and it is probably not infectious. Okay. And this is the sample result from a local lab. They'll report it as E-gene CT value 37.08. When it says the RDLP gene is not detected, that means it is more than 40. And this N gene, the CT value is 39.38. In this kind of result, we will interpret it as the end stage of the infection. So the Institute for Medical Research have shown that if you put this virus sample into cell culture, you cannot regrow the virus. The virus is actually dead, right? So this is a lab phase of infection. So this is also RDRP 36, and the 3 genes, they are in the 30s. This is also considered lab phase of infection. When it comes to this, the E-RDLP, these are in the 20s. So the number of the genome can be detected much earlier. So when you see your result in the 20s or below 20s, you are highly infectious because the viral load is high. Okay. And you see that this laboratory, they are using a different system, the N operating 1, AB, and SG. Basically, if you don't understand them, it doesn't matter. You just need to know one of them is for screening and the other 2 is for confirmation. And the CT value will not lie to you. This is the maximum CT value will always be 40. And this in the 19 and 20s will be extremely high in viral load. Antigen test is another way that we can test whether we're infected or not. Is also known as a lateral flow assay, something like a pregnancy test kit. It is looking for the virus nucleoprotein rather than the genomic RNA. It is less sensitive than molecular assay, but since it is less sensitive, if you do it yourself, like using the saliva home test, and it is positive, it is extremely highly likely that you are positive, okay? But if you just been exposed to a person and then you test it with saliva test kit or even PCR, it will be negative. You need to test it the second time after a few days. The lateral flow assay, what we normally call it the qualitative antibody assay, sometimes they will only give you the quality. The result is positive or negative. And this is antibody test. The lateral flow assay looks identical, but it's really looking for something else. It's looking for your antibody. Probably this is something of interest because of the current vaccination drive. It detects antibody against N or S. You need to really understand the kit that you are using rather than just tag anything that comes along. It is less sensitive. We don't really use this for to confirm infection because antibody develop much later. Because antibody produce late and high false negative. And you will see that this IgM, IgG plus is a new one. It actually detects the presence of the spike RBD, the right receptor binding domain, IgG. So if you want to know if your vaccine works or not, this should be the way. And the vaccine that we have received, those with Pfizer, you are being injected using a mRNA which targets a spike. And this spike protein will produce antibody against the receptor binding domain. Okay, Sinovac, it uses a whole virus that has been killed. So your body generally will produce antibody against N and S, both of them. And AstraZeneca is a spike only. The types of antibody test is qualitative. Letter 4, you get positive or negative. And quantitative, it uses a different type of test which requires large equipment. The result is represented in like international unit per mil, arbitrary unit per mil. And these are non-harmonized systems. There are quite a number of people, they ask me, hi, I went to this lab and I get 50 IU per mil. And somehow they see that in my study, which uses AU per mil, a lot of people have much higher antibody level. And 50 for mine is actually a negative. So these are non-harmonized. It cannot be compared. This is the results. Basically, the amount of antibody is being counted and presented in arbitrary unit per mil. So in this case, this guy has 3,000 plus antibody unit. And it's positive when the measurement is 50, okay? And for my study, 840 AU per mil is the amount of antibody that a person who wish to donate his blood for plasma therapy, you must have at least 840 AU per mil. Otherwise, they won't take you. So this plasma therapy is not recent. It's being used to harvest the antibody from someone who have been vaccinated or recovered from a real infection to use the antibody to treat other people, okay, who have been down with severe COVID. And this result is from another lab. The top one is Antigen positive. So the reference range is negative. And this kind of interpretation sometimes makes people alarmed whether they are infected or not. If you have been vaccinated using Sinovac, you will have, or most people will have anti-N antibody. And this will be positive. If you have been vaccinated using AstraZeneca or Pfizer, it doesn't contain anti-N, so this should be negative. But if you have been infected before vaccination or infected after your vaccination, this value is positive, okay? So we can use this to differentiate a vaccine-derived antibody or virus-derived antibody. The anti-SARS-CoV-2 anti-S, this person has 50.5. So if you are using this number without referring to the unit per mil, then you are in trouble because my 50 is using the Abbott architect system, 50 is actually negative. but this is using a Roche system. It's a different system. Okay. This is the end, but I'm sure many of you have tested your antibody. You pay good money to get your antibody tested. If you say whether it's worth to test your antibody level, it really depends. Because the units, they'll give you like in the 50 units, you know it's positive. If you get 500, it's good. But if you don't have a population data to support your quantitative number, it is actually as good as, yes, you have antibody, and no, you don't have antibody. It becomes, the interpretation becomes qualitative. For quantitative antibody analysis, it should be 2 points. One, if you get it done today, then you should get another one a month time or 2 months time. Then you get 2 points to see whether the antibody actually decreases or increases. Because the antibody for SARS-CoV-2 from the vaccine and from the real infection, it will not last very long, as you know. Okay. I hope this helps you to understand a little bit about the vaccine and diagnostic. I'll open the floor for question.
Yeah, thank you, Kenny. We've got